All right, hello everyone, and welcome to my channel. This is a channel for educational purposes, and we look at theories of everything primarily, cosmologies, all-encompassing theories that could help you out if you knew about them, help out you with your paradigm shifting or with your overall holistic gestalt. And today is our 392nd video on Dewey B. Larson and his reciprocal system of theory. And Larson lived in the 20th century in the US, and around 1959 he proposed his two fundamental postulates and about how the universe operated. And then he took those two postulates and through a process of deduction, kind of if this then that approach, he derived an entire theoretical universe about how what the universe would look like if, in detail, if my postulates are correct. And it turns out that the universe that he recreated, or that he created in his own head through theory, remarkably resembles the actual empirical universe that has been measured and documented by the legacy scientists. So, because of that, I think that Mr. Larson's work deserves an investigation, a hearing, and we've been looking at a lot of his books, his articles, some of his followers, books and articles, and today we are reading, we're going to start reading a paper that Larson gave back in 1978 called Fundamentals of Science in the 21st Century. Before we get started, I'd just like to give you a quick once-over on the reciprocal system. Larson's two postulates are both very brief. The second postulate is not as important as the first, so I'll just lead with that one. The second postulate is that the universe conforms to the relationships of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. And there has been some dispute about that postulate from within his own ranks. His own followers many of them have rejected the concept of Euclidean geometry in particular, but other parts of it as well. But the first postulate is where, more of maybe the mainstream people are taken aback, and that is that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. If I were rephrasing that, I would say the universe is made out of motion. Well, I would say the universe is not made out of matter. It's not made out of energy. It's not made out of force. It is made out of motion. And specifically, it's made out of a non-directional kind of motion called scalar motion. And motion is the relationship between space and time. Space and time are reciprocals of one another. They have all the general qualities of reciprocals. They have the same qualities, except in reverse order. They do not exist in and of themselves, only together in motion. Motion is basically a fraction with space or time as the numerator and time or space as the denominator. All of our scientific quantities, our units, so to speak, are fractions with space or time as the numerator and time or space as the denominator. Scalar motion is a specific kind of motion that has been curiously uninvestigated by the researchers, scientists out there, even though they know of its existence. It is best modeled, or maybe not best, but it is modeled by a balloon with dots on it. If you blow up the balloon, all the dots are moving away from each other. But they're not moving in any specific direction. And so that is scalar motion. You can also think about it in terms of time. Time is always getting later and later and later and later. But it's not getting later in any specific direction. So Larson refers to these as clock time and clock space. Space is always getting later and later and later. Or time is always getting later and later and later. Space is always getting farther and farther and farther apart. But time and space also have their three-dimensional aspects, which are somewhat fictitious. Coordinate space and coordinate time. We see coordinate space all over the place. It's part of our reality, as is clock time. 3 dimensions of space, x, y, z coordinates in a stationary frame. But because reciprocals have the same qualities, Larson also, arrives at the conclusion that time has its 3-dimensional aspect, stationary, 3-dimensional time coordinates. Maybe not x, y, and z, but perhaps I, j, and k. And he refers to that as coordinate time. And then space and time only come in discrete units. They are quantized, as is motion. You have to have full units of space and time before you have either of those things. And if you have exactly 1 unit of space in 1 unit of time, you have the speed of light. The speed of light is what Larson calls unit speed. 1 over 1 equals 1. And this unit speed is the background motion of the universe of motion of Larson. If you have a nothingness, in Larson's universe, if you have a nothingness, you have motion at the speed of light in all directions, outward. And so that is the null point, or the 0 point, or the neutral point, or the reference point. Larson refers to it as the progression of the natural reference system. So in Larson's system, we have a reference system that is moving outward at the speed of light in all directions, unlike the legacy scientists whose reference system is stationary. And in a similar way, we have a balance. So the 1 is the center of Larson's universe, whereas 0 is the center of the scientist's universe. 1 is, balanced on one hand, on the positive side by 2, 3, 4, and 5, and on the negative by 1/2, 1/3, 1/4, and 1/5. Unlike the legacy scientists whose center is 0 and balanced by 1, 2, 3, 4, and 5 on one side, and -1, -2, -3, -4, -5 on the other. Just like a reciprocal, 1 being at the center. And that 1 is the speed of light in all directions moving outward. And so that means that half of the universe is moving faster than the speed of light, which flies in the face of legacy science, including Einstein, who said that the speed of light is the maximum speed of the universe. They didn't know anything about this faster than the speed of light sector of the universe that Larson refers to as the cosmic sector. He refers to our familiar, slower than the speed of light sector as the material sector. And the material sector has a reciprocal relation to the cosmic sector, as you can see by the fact that in the material sector, you have relations that are based on 3 dimensions of space, clock or coordinate space, and the clock is always getting later and later and later. Clock time. That's the material sector. But in the cosmic sector, across that speed of light boundary, you have coordinate time, 3 dimensions of stationary time, and clock space. Space is always getting farther and farther and farther apart. So they are the same generally, but they are in the roles of space and time are reversed. Okay, we're going to get started here with this paper, The Fundamentals of Science in the 21st Century. And I think here Mr. Larson will also, clarify a little bit more how the reciprocal system works. Now, this paper is too long to do in one episode. We'll probably have to spread it out over 3-4 episodes. But here it goes. As you've noticed, it took a little while for the CBS crew to set up this evening. I don't exactly know if that's this talk took place in Salt Lake City, which is kind of where the center of the reciprocal system operation is, and this is the 3rd annual NSA conference, not the federal NSA spy intelligence organization, but the New Science Advocates. And it's also interesting that the reciprocal system, a lot of their stuff is put on by the ISUS group, ISUS, the International Society for a Unified Science. So apparently there is a camera crew there from CBS. And on that account, we're running at least half an hour late. So I'm going to omit the first half an hour of what I was going to say. It's unfortunate because I will include some of my most shady jokes. But I'll try to take up from that half-hour period. Frank took you back into history quite a little way, but just to do him one better, I'm going to go still farther back. 5,000 years ago, when the invention of writing on clay tablets by the Sumerians first gave the human race an opportunity to leave a permanent record of its thoughts and actions, there was already in existence a rather sophisticated science of astronomy. The priests, who were the scientists of those days, were not only familiar with elementary astronomical facts, such as the apparent movements of the sun, moon, and planets, but they had also advanced to the point where they were able to predict eclipses and to calculate the length of the year to within about a half hour of its present accepted value. The premises upon which these calculations and others of the same kind were made were the fundamentals of science of that day, in the sense in which I am using the term now. That is, they were the most basic of the principles that were used by the science of that day. These principles were originally derived by a simple application of what we now call inductive reasoning. That is, they were generalizations from experience. And that is the most reliable method of arriving at scientific principles, fundamental or otherwise. But unfortunately, it is limited by the amount of empirical information that's available and by the extent to which that information has been analyzed. So the result is that an inductive science, such as that of the ancient peoples, has a tendency to fall behind the progress of empirical discovery, and ultimately it acquires a rather embarrassing accumulation of unsolved problems. Now, that was the situation in Egypt, in Babylonia, and in the Far East about 3,000 years ago. The time was clearly ripe for some new approach, and that was provided by a remarkable group of thinkers who flourished in Greece during the golden age of that country's history. A source of order in the universe, these men said, was mind. And the proper way of arriving at general principles was to apply insight and reasoning. The result of that change in policy was to concentrate attention on the causes of physical phenomena rather than on the phenomena themselves. Where the Egyptians saw only the fact that a rock falls if it's released from a height, the Greeks looked for the cause of the fall. Now they reasoned that everything must have its natural place. So the rock in falling is merely seeking its fixed natural place. In this way, by providing an explanation for what happened, they remedied the chief defect of the previous inductive theories. Similarly, they reasoned, as Professor Meyer indicated, that while the earth is obviously imperfect, the heavens are perfect, and all heavenly motions must then take the perfect form of that of a circle. So the orbits of the planets are undoubtedly circular. Now, observation and experiment were definitely relegated to a secondary position by the Greeks, but they were not disregarded altogether. So when the observation showed that the planetary orbits are not exactly circles, it was recognized that there was an awkward discrepancy that we have to do something about. But one of the strong points of an inventive science, such as that of the Greeks, is that it can easily accommodate new discoveries simply by more invention. Greek method of deriving scientific principles by pure invention doesn't quite make sense, but Greek method of deriving scientific principles by pure invention is that it lends itself readily to the assimilation of new information by means of more invention. So they assumed that the planets move in small circles called epicycles, and these epicycles then move around the main planetary orbit. Then, when further observational refinement disclosed still more discrepancies, those could be taken care of in exactly the same way, merely by adding more epicycles. This Ptolemaic theory of planetary orbits is typical of inventive theories in general. And since we see it in a historical perspective by taking a look at this Ptolemaic theory, we can get an idea of the general characteristics of inventive theories. The first point that we need to note is that that theory was mathematically correct within the existing observational limits, the then existing limits. That is a general characteristic of all inventive theories because they're invented for that specific purpose. They're specifically designed to fit mathematics that are already known. The second significant point is that theory, the Ptolemaic theory, was conceptually wrong. The interpretation of the mathematics was wrong. That, again, is a general characteristic that applies to all inventive characteristics of invented theories because of the circumstances under which they're invented. As many observers have pointed out, long-standing problems in science do not continue to exist because of a lack of competence on the part of those who are trying to solve them, nor do they continue to exist because of a lack of methods by which to go about solving them. They continue to exist because some piece or pieces of information that are essential are missing. In the case of the Ptolemaic theory, there were two such pieces of information. The Greeks did not realize that the planets revolve around the sun rather than around the earth. And they did not know that there is a force of gravitation controlling those movements. Without those two pieces of information, neither the Ptolemaic theory nor any other theory that was invented to explain the mathematics could have been correct. Now, that is a general characteristic of inventive theories, and I am stressing it at this time because it will be important later on in other connections. If the information is available, if all the essential information is there, then there is no need to invent a theory. Then we can obtain it by inductive means. If the essential information is not there, then any theory we invent cannot be conceptually right. In view of the practically unlimited opportunities for making additional ad hoc assumptions to meet any situation that may arise, an inventive science never reaches the kind of a situation that causes the downfall of inductive sciences. At any given time, there may be a few items for which plausible explanations have not yet been invented, but there is never the large accumulation of unexplained phenomena that characterizes an inductive science that has fallen behind the progress of empirical investigation. However, the freedom to meet new requirements by adding more and more ad hoc assumptions or epicycles leads to a fate of a different kind. The time ultimately comes when such a system of theory simply has too many epicycles. In the meantime, even though the fundamental theories in current use are inventive, the accumulation of empirical information and the construction of inductive generalizations of a lower rank continues. Ultimately, a point is reached where the principles derived inductively are sufficiently broad in their scope to challenge the premises of the prevailing inventive theories. The Greek system reached this point about 500 years ago. And science then reverted to the inductive status, disregarding or discarding inventive concepts such as the perfection of the heavens and the natural places of physical entities, in favor of principles formulated by such men as Kepler and Newton through inductive reasoning from observed and measured facts. With the benefit of all the empirical information accumulated during the approximately 2,500 years since the demise of the earlier inductive systems of the ancient civilizations, the new inductive science was a vastly improved product, and it scored some remarkable successes. At one time, its practitioners were quite confident that a complete understanding of the universe was within their grasp. But here, again, the inherent inability of an inductive system of theory to keep pace with the progress of empirical discovery asserted itself. Eventually, Newtonian physics was confronted with a series of discrepancies for which it had no plausible answers. Another reversal of policy took place, and the inductive science of Newton and his contemporaries was replaced by a science based on invented principles, just as the first inductive sciences were replaced 3,000 years earlier by the inventive system of the Greeks. When an idea or system of ideas gains general acceptance and becomes a familiar feature of current thought, its origins recede from view, and it is quite likely that many a reader may be reluctant to believe that the basic theories of modern physics, the relativity theory, for instance, belong in the same category as the Ptolemaic theory of astronomy. But all of them belong in the category of pure inventions. The originators of modern theories do not deny this. Indeed, they emphasize it. Einstein, for example, saw the general acceptance of his theories in just the way that I have described, a victory of inventive science over inductive science. In his opinion, pure invention is the only way in which true fundamental principles can be derived. Einstein was highly critical of Newton's attempts to derive such principles inductively. He said this, quote, "Newton, the first creator of a comprehensive, workable system of theoretical physics, still believed that the basic concepts and laws of his system could be derived from experience. The tremendous practical success of his doctrines may well have prevented him and the physicists of the 18th and 19th centuries from recognizing the fictitious character of the formulations of his system." End quote. Einstein's own view was that the basic concepts and laws of physics, what I am calling the fundamentals, are, quote, "in a logical sense, free inventions of the human mind," end quote. He elaborates this view in these statements taken from the book, The World as I See It. Quote, However, sense perception only gives information of this external world of physical reality indirectly, we can only grasp the latter by speculative means. The theoretical scientist is compelled in an increasing degree to be guided by purely mathematical, formal considerations in his search for a theory, because the physical experience of the experimenter cannot lift him into the regions of highest abstraction. The axiomatic basis of theoretical physics cannot be extracted from experience, but must be freely invented. There is a rather general tendency to assume that Einstein and the other architects of modern science, I guess that was the end of the quote after abstraction, so let me go back here. The axiomatic basis of theoretical physics cannot be extracted from experience, but must be freely invented. Okay, that's the end of the quote. There is a rather general tendency to assume that Einstein and the other architects of modern science were not actually as casual about the background of their theories as these words would indicate, that their basic principles must have been anchored to something solid at some point. But this is not true. As Rudolf Carnap puts it, these theories were, quote, constructed floating in the air, so to speak, end quote. Einstein gives us enough information about some of his concepts to make it clear that when he talks about free invention, he means exactly that. For example, the propagation of radiation plays a very important part in his theories, and his comments about the explanation that he invented to account for the mechanism of propagation and its relation to space are therefore very significant. In one of his books, he tells us that the formulation of a theory to account for this phenomena is a very difficult task. And he concludes with this statement: the only way out, quote, the only way out seems to be to take for granted the fact that space has the physical properties of transmitting electromagnetic waves, and not to bother too much about the meaning of this statement. The point of all this is that the invented theories of present-day science have exactly the same logical standing that the Ptolemaic theory of astronomy, the natural place theory of gravitation, and the other theories invented by the Greek scientists had in their day. They are mathematically correct, but conceptually wrong. Okay, we're going to leave it there and start up tomorrow from there. We might just reiterate that last paragraph before we get started. But I do like the way that Larson does his history of science, and he tends to kind of defeat the legacy scientists with their own words, like he's doing here. And so we will learn more about this tomorrow as we approach. And thanks for tuning in today. Have a great day.